Welcome to the world of Fourier analysis. In this presentation, we're going to explore the fundamentals of Fourier analysis and how it's used across various fields. Get ready to discover how complex waves can be broken down into simpler components, unlocking insights in signal processing, music, and even quantum mechanics. So, what exactly is Fourier analysis? It's a mathematical technique that decomposes complex signals into simple sine and cosine waves. Think of it as a prism for sound or any other kind of signal, separating it into its basic color or frequency components. Fourier analysis reveals the frequency components hidden within any signal. Any periodic function can be expressed as a sum of sines and cosines. The formula shown here is f of x is equal to sigma a subscript n sine of nx plus b subscript n cosine of nx. At the heart of Fourier analysis lies the Fourier transform. The Fourier transform transforms signals from the time domain to the frequency domain. The formula shown here is f of omega equals integral of f of t times e to the power negative I omega t dt. In the time domain, we see how a signal changes over time. But in the frequency domain, we discover which frequencies are present in that signal. Fourier analysis is essential in signal processing. It allows us to filter audio, removing unwanted noise and enhancing specific frequencies. It is used in communication for modulation and demodulation of radio signals. Medical imaging techniques like MRI and CT scans also rely on Fourier transforms to generate clear images. In the world of music, Fourier analysis is a game changer. It helps in pitch detection, allowing us to identify fundamental frequencies in music. Audio compression formats like MP3 and AAC use frequency analysis to reduce file sizes. And equalizers use it to boost or cut specific frequency bands, shaping the sound we hear. Believe it or not, Fourier analysis also plays a crucial role in quantum mechanics. Wave functions, which describe quantum states, are analyzed in both position and momentum space. The uncertainty principle, a cornerstone of quantum mechanics, is mathematically connected through the Fourier transform between these position and momentum representations. The Schrödinger equation shown here, IH bar partial derivative psi by partial derivative t equals h cap psi, describes how wave functions evolve over time, and Fourier transforms are used to analyze these wave functions to understand quantum behavior. The Fast Fourier Transform, or FFT, is a game-changer in computation. While the standard discrete Fourier transform, or DFT, has a complexity of order n squared, making it slow for large datasets, the FFT algorithm achieves the same result with a complexity of order n log n. This is a revolutionary speed-up. Shown here is how we can implement FFT using SIPI library. We can use sipi.fft.fft to get the FFT result of a signal. To get the FFT result of a real-valued signal, we can use sipi.fft.rfft method. Let's recap the key takeaways from our exploration of Fourier analysis. It's a universal tool that decomposes any signal into its frequency components, providing insights into its structure. The FFT revolution has made real-time analysis possible across various industries, from telecommunications to finance. Fourier analysis has wide-ranging applications from music production to quantum physics, demonstrating its versatility and importance. And finally, it acts as a domain transform, bridging time and frequency perspectives, and offering a comprehensive understanding of signals and systems. Fourier analysis reveals the hidden frequency structure in complex waveforms, enabling breakthrough innovations across science and technology. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.